All right, let's look now at electromagnetic radiation. Now, thermal energy can be transferred by radiation, and you can see here the stove element glowing red. There's radiation that's coming off of that element that we interpret as quote-unquote heat. Now, even when the stove element is cooler, it's still emitting thermal energy, radiant energy. It's just that it's no longer emitting in the visible part of the spectrum. So the visible spectrum runs in frequency terms from about 420 trillion hertz up to about 770 trillion hertz. Many objects at room temperature are emitting in the infrared part of the spectrum that our eyes do not detect. Now, objects don't actually emit one frequency, so this stove element glowing red is not just emitting in around 420 terahertz. There's actually a range of frequencies it'll be emitting over. The most common frequency may very well be 420 terahertz, but there will be some shorter wavelength infrared, and there'll be some longer wavelength ultraviolet there as well. So, that most common frequency, that peak of the distribution, is actually proportional to the temperature of the object. And there's a principle known as Wean's law, which just says that the maximum frequency is a constant times the absolute temperature. Now, by the absolute temperature, we mean the temperature in degrees Kelvin. And you may recall that to get Kelvin, you take the degrees centigrade and you add 273 degrees to that. If you want to be picky, it's 273 plus 273.16, I think. Now, there's a coefficient of proportionality there, which the value is given here. This converts from Kelvin to gigahertz. So if you have a star that's emitting mainly yellow light, let's say that's about 500 terahertz, you can work backwards and find its surface temperature. If a maximum frequency is a constant times temperature, then the temperature will be the maximum frequency divided by that constant. So we've got 500 terahertz, and this coefficient of proportionality is 58.79 gigahertz per Kelvin. Now, tera to giga is an extra factor of 1,000. And then we've got 500 over 58, so that's going to be about 0.9. So we're expecting something around 900 Kelvin or so. Let's work out that value. Okay, so that's 8505 Kelvin, about 8,000 Kelvin. Which is not atypical for stars. They're usually in the, the range of several thousand Kelvin in terms of surface temperature. Now, if we add up all of the frequencies and add up all of the energy for all of that, every little bit of frequency that the hot object is emitting, then you'll get an expression for the total energy, the total intensity of radiation that it's emitting, and that ends up being proportional, if you do the calculus, to the fourth power of temperature. And there's a little constant here. It's actually Greek letter sigma. And sigma is just a constant. Now, intensity, you may recall, is the ratio of power to area. So a power is an intensity times an area. And so the result we get from calculus is the intensity is sigma t to the fourth, and then we multiply that by an area. That area is the surface area of the object. So what we find then is that the power an object is emitting is a constant times its surface area times its absolute temperature to the fourth. So T is the object temperature in Kelvin, so you take centigrade, add 273. A is the surface area in meters squared. P is a power, okay, in watts. Not watts per square meter, but watts. And then this little sigma is 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. Now that's for an ideal radiator. We're going to modify that for something that's not quite ideal. But first, there's another thing to keep in mind, and that is that the object, if it's sitting there, not only is it radiating infrared thermal energy, it's also absorbing it from the surroundings. And the surroundings will be emitting in a similar sort of way, something that depends on their temperature to the fourth. So we arrive at then the fact that there's going to be a net transfer of radiant energy, which will depend on the object temperature to the fourth minus the surroundings temperature to the fourth. So this is the emission, and then this represents absorption of energy from the surroundings. Now, if the object is not an ideal absorber, then we'll multiply by a constant called the emissivity, which represents the percentage ideal absorber behavior. And that's a Greek letter epsilon that represents that quantity. So if, for instance, you've got an emissivity of 0.1, that's only 10% ideal absorber. That means only 10% of the radiant energy impingent on the object is going to get absorbed. The other 90% is reflected. And so, white objects typically are very reflective, so this might be a white object. With an emissivity of 0.7, that means 70% of the incident energy is going to get absorbed, and about 30% will be reflected. Now, the thing about emissivity is that it not only does it depend on surface condition, but it also depends on what sort of radiation is impingent on the object. So, for instance, human skin is a really good absorber. It's got a really high emissivity in the infrared, but it's very reflective in the visible. That's why it's shiny and pinkish, at least for Caucasians. Similarly, so if we plot a graph here, right here you see Caucasian skin has a fairly low emissivity because it's reflective in the visible light, but in the infrared it's highly absorbing. Similarly, green plants absorb pretty well, except in the green where they reflect, and that's why they look green. So the emissivity actually varies depending on the frequency of the light, and we actually will end up introducing a variable known as the albedo that reflects the average of emissivity over an entire range of wavelengths. So if we include that emissivity factor, to say that not everything is a perfect absorber, we get the following statement of radiant power. Here's the emissivity constant. This is Stefan's constant, this value here. Here's the surface area. So this is emission by the object. This is absorbed from the surroundings. This is the net radiant power. So as an example of how to use that law, we'll put a hot concrete block in a sauna. And let's find the net rate of radiant energy transfer. So by Stefan's law, that's going to be the constant, 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth. The emissivity constant is given as 0.65. The surface area is 0.15 square meters. And then let's work with the temperatures here. The object is 120 C. Now we have to add 273 to make it Kelvin. That's 393 Kelvin. And then the surroundings are 35, so you add 273, and that's 308 Kelvin. And not only do you fourth power the number, but you fourth power the Kelvin. The Kelvin to the fourth cancels out, meters squared cancels out, and we end up with an answer that's going to be in watts. Let's just pause and calculate that. Okay, so that ends up being about 82.1 watts, about 82.1 joules per second of energy will be emitted by that concrete block because it's hotter than the surroundings. Okay, next up. Oh, yes, okay, so we've got the sun, and there's the sun's surface temperature, and there's its radius. How much power does it emit? Well, we know that we can calculate the radiant energy, net rate of radiant energy transfer. Sigma epsilon surface area object temperature to the fourth minus surroundings to the fourth. So we've got the surface temperature of the sun here. And again, you see that 6,000 Kelvin. Earlier we calculated a different star. I think it was like 8,000 Kelvin. So they're in the same order of magnitude. The temperature of the surroundings, well, space is basically at 0. If you know a little bit about astronomy, you know it's actually 3 Kelvin, but that's so small that we can ignore it. And the radius is useful because the surface of a sun will be a sphere, and the surface area of a sphere is 4 pi r squared. So we need to know the radius of the sun. So this will be a big long calculation. We won't bother with the units because we did that last time. We'll treat the sun as if it's got an emissivity of 1. That should be given in the problem. So here we've got 4 pi, put in its radius, 6.95 times 10 to the 8 squared. And then this is going to be 5839 to the fourth minus 0. So let's pause and calculate that. Okay, so that gives us 4.00 times 10 to the 26 watts, or that's 400 times 10 to the 24 watts, and believe it or not, 10 to the 24 is a yotta. So it's 400 yotta watts. That's joules every second coming from the sun. That's a significant amount of energy. Now that energy spreads out over a heliocentric sphere as that radiation moves away from the sun at the speed of light. So that energy, obviously, as you get further and further from the sun, is going to become more and more diluted. That means the intensity is going to be reduced. Now, way out here where the Earth is, the Earth presents a circular area. There's a little tiny circle there that intercepts radiation from the sun. And we're basically interested in knowing how much energy is the Earth intercepting, what is the intensity of the solar radiation here. Now, we define intensity, remember, as the ratio of power over area. Now, with big R as the sun's orbit, and with P naught as the radiant energy from the sun, that's the 400 yottawatts, this is going to be P naught over 4 pi big R squared, where R is the distance from the sun to the Earth. Now, that is 150 million kilometers. It's 1.5 times 10 to the 11 meters. So we put in the 400 yottawatts, or the 400 times 10 to the 24 watts, or 4 times 10 to the 26 as it's given up there. And then we divide by 4 pi, 1.5 times 10 to the 11 meters squared. And let's just pause and calculate that. And we see that that works out to about 1,400 watts per square meter. So for every square meter of area here on the sun, on the heliocentric sphere, at one astronomical unit, 1 Earth-Sun distance away, every square meter of area here would get 1,400 watts. That's 1,400 joules every second of solar energy arriving at that point. Now the Earth has got lots of meters squared there that it provides to intercept that solar radiation, so there'll be lots of watts hitting the Earth. But this is for every square meter. Now, as it, in order to reach the surface of the Earth, that radiation actually has to pass through the atmosphere. And therefore, that 1,400 watts per square meter is actually a little bit less by the time it reaches the surface. And the typical number we use is usually around 1,000 watts per square meter. There's several reasons why the 1,400 gets reduced to 1,000 down here. The first is that some of the solar radiation actually reflects off the atmosphere. So here's the Earth, here's the atmosphere. This is the top of atmosphere, the TOA. And some energy just reflects right off the top. Okay? Now, there's also scattering. There's tiny little bits, tiny molecules up here in the upper atmosphere called aerosols, tiny, tiny little molecules, and they will actually absorb solar radiation, and then the solar radiation will get scattered in all directions. Okay? And because some of it gets scattered back into space and not down to Earth, that also reduces the intensity we get here. Lastly, some of the molecules of gas in the upper atmosphere will actually absorb that radiation, and that will put them into a higher vibrational state, so they'll vibrate back and forth. And that energy then absorbed by the atmosphere, and then not reaching the surface. So we've got reflection, scattering, absorption by the atmosphere. Now, there's other factors, other reasons why the 1400 out here gets reduced to 1000 on the surface. And latitude plays a role as well, because if you've got, say, a cylinder of light from the sun that's hitting pretty much dead on, then you're going to have a higher intensity. But up here at a higher latitude, that energy is going to get spread out over a much larger area on the Earth. And with more area, it's less intense. Remember that intensity is a power over an area. So if that sunlight is being spread out more, then it'll be less intense. So, 1400, well, at the equator, this isn't a factor, but up here at higher latitudes, it certainly is. And of course, ultimately, this is why it gets cold in the winter, especially, up here in Canada, because we're at a higher latitude, and therefore the sun's energy gets spread out over a really large area. It's less intense. The days and nights cool down, and so on and so on. Now, this same effect applies to time of day. So if we think of this as the North Pole, then this shows the latitude effect. But if we imagine the North Pole is here at the center, and that the Earth is rotating this way, then we also see time of day matters, because this cone of light here would be at noon, so you've got really intense light at noon. But then as the Earth rotates, and as you move, say, from here at noontime in Vancouver to over here where the sun's about to set, then your solar energy, as it spreads out, is getting less intense, and that's why you don't get sunburns in the afternoon. So latitude and time of day effects further reduce the intensity from the 1400 out here down to 1000 on the Earth's surface. Now, again, with latitude, not only do you have that spreading out of the area, but you've also got a greater distance through the atmosphere. So the thickness of the atmosphere, of course, is the same, but here, this is going to be greater than the thickness of the atmosphere. This is just the thickness of the atmosphere. So you're actually going further through the atmosphere when you're at higher latitudes, and therefore those effects that we discussed earlier, absorption, scattering, and absorption and scattering, are greater as you get to higher latitudes. And so all of these factors together reduce that 1400 watts per square meter down to a typical value of about 1000. Now, it does depend on latitude. And so if you were to compare us, at around 49 and Phoenix at around, must be low 30s. In Phoenix, say in the summer, you'll find the solar intensity gets really high. And you might get a graph like that. Vancouver, being at a higher latitude, we won't get that maximum intensity. It'll be lower. The thing about Vancouver, though, say in the summer anyway, is we actually get a longer day than Phoenix does. So this might be two curves in the summer, right? So this would be the Phoenix, and this would be the Vancouver. Phoenix has a greater maximum intensity simply because in the summer, with the Earth tilted towards the sun, Phoenix gets sun pretty much directly overhead. Vancouver, no. Okay? Vancouver, the sun reaches maybe an angle of maximum 60 degrees in the sky in the summer. Phoenix, it gets up to the high 80s, so it's basically directly overhead. So, and if we were to do this in the winter, it would be reversed. The day in Phoenix doesn't change very much, but the Vancouver day would be a shorter day. So in the summer, first of all, they'll both be less than they were before, just because now the sun is, now we're tilted away from the sun, and now down here, south of the equator, they have maximum intensity. So Phoenix intensity has dropped too. So this might be this peak here. Let's call it intensity summer, something like that. And so in the winter, the sun's not going to be as intense in Phoenix. And then Vancouver will have a shorter day. So it would be Phoenix and Vancouver. So this would be wintertime. Now that matters if you want to try and capture energy from the sun. For instance, by a solar panel. Because if you take everything into account, weather patterns, latitude, night and day, 24 hours a day, 365 days a year, you'll get about 100 watts of energy for every square meter in Vancouver. And about 3 times that for Phoenix. So let's imagine that you want to buy a solar panel and make some electricity. Typically their efficiencies are about 15%. Let's imagine that you want to do this in Vancouver. So the area of your panel is 2 meters by 3 meters. That's 6 square meters. So in Vancouver, the average intensity averaged over the whole year, and again this is 24, 365, it's about 100 watts for every square meter. You got about 6 square meters of panel. That's a pretty sizable panel. That'd fill up your roof pretty good. So taking everything into account, the cloudiness, the latitude and everything, that's about a 600 watt panel. And then you're going to find the annual power. Sorry, it should be the annual energy, not the annual power, because this is the power. So the energy will be the product of power and time. We're making 600 joules every second. The time is a year, and there's 31.536 million seconds in a year. So let's just see how much energy we make. So we make 18,921 megajoules. Because the seconds cancel. So we made about 18.9 gigajoules of energy from our solar panel. Now, if you've got, or if you recall, the residents will use typical residential energy use in Canada is about 105 gigajoules. So as a percentage, you're getting, something like about 15% there. So 18.9 divided by 105, come on you, 18.9 divided by 105, yeah, 18%. So that's a worthwhile percentage of your residential energy. Now, how much money are we saving compared with what we would pay for electricity in our home, which is about 7 cents per kilowatt hour? So solar panels now are between $1 and $3 a watt. So 600 watts, let's say it's going to cost you $1,500 installed, and it's going to last about 10 years. So your cost is $1,500, and you're getting 18.9 gigajoules per year. But don't forget, it's going to last 10 years, so you're going to have 10 times that. So you're going to have 189 gigajoules over the lifetime of the panel. So we got 1,500 joules over 189 gigajoules, and we just want to compare that with 7 cents per kilowatt hour. So let's have a look here. So this is going to be 1,500 divided by 189. So we're getting about $7.94 per gigajoule. That's a pretty good price. Remember, natural gas, we pay about $5 per gigajoule. So here we're paying a little bit more. But 7 cents per kilowatt hour. Now, a kilowatt hour is 3.6 megajoules. And there's 1,000 megajoules in a giga. So mega will cancel, kilowatt hours will cancel. So this is 7,000 cents or $70 divided by 3.6. So So let's see what that is. 70 divided by 3.6. That's $19.4 per gigajoule. So this would be the residential rate for electricity, and you would pay that for 10 years. And by the end of those 10 years, you'd certainly be further ahead with the solar panel, because averaged over 10 years, the cost of the electricity would be $7.94 per gigajoule. So the solar panel will definitely pay for itself, provided it lasts the 10 years that's advertised.